All right, let's get started. We're about to go on a pretty wild journey into one of the most complex, most mysterious objects in the entire universe, the human brain. And we're not just going to look at it from the outside. We're going in, all thanks to some unbelievable technology. Okay, let's just dive right in. Take a good look at your screen. What do you think this is? It's pretty abstract, right? Almost like a ghostly image floating in the dark. Any guesses? If you were thinking it's a brain, you are absolutely right. This is a literal peek inside a living human head. So, how is that even possible? Well, in this first part, we're going to explore the tech that makes this incredible map of our inner world. The magic behind this is something called magnetic resonance imaging, or as you know it, MRI. Now, the main thing to get here is that it uses super powerful magnets and radio waves to see inside the body. It's a totally non-invasive way to get these stunningly detailed pictures of our anatomy. So, an MRI doesn't just snap one big 3D photo. Nope. Instead, it takes hundreds of individual, super thin 2D images, or slices. The best way to think about it is that each image is like a single page in a book. And when you flip through all those pages, you get the whole story, the entire structure from front to back. And that is exactly what we are about to do. So get ready. We're taking a virtual tour, moving right through the brain, slice by slice. Okay, here we go. We're starting from the absolute outermost edge of the head. And already you can start to see those complex folded structures of the brain beginning to appear. As we push in a little deeper, the main structures start to come into focus. Look at that incredible wrinkled texture. That's the cerebral cortex. Now keep watching because a really clear landmark is about to appear. And there it is. That distinct circle is the eye socket. And you can even see the optic nerve trailing back from it, heading deep into the brain. We're getting close to the core now, pushing toward that central midline where everything connects. And there we are, a perfect cross-section, right at the very center of the brain. What an absolutely incredible view of our own inner world. Okay, that was a quick fly-through. Now that we've arrived, let's just pause on this central image. In this next section, we'll get our bearings and identify some of the key landmarks in the anatomy of a thought. This view, by the way, is called a sagittal view, and it's perfect. It gives us this fantastic profile of the brain's major components, all lined up and visible at once. So, let's break this down. That giant wrinkled area up top, that's the cerebrum, the command center for your thoughts and actions. Tucked underneath at the back is the cerebellum, which is the master of physical coordination and balance. See that part extending down? That's the brainstem, connecting to the spinal cord and handling all the vital stuff you don't think about, like breathing. And see that bright C-shaped band right in the middle? That's the corpus callosum, a superhighway of over 200 million nerve fibers connecting the left and right halves of the brain. This side view is incredibly useful. But for any doctor or researcher, one angle is never going to be enough. To really, truly understand what's going on, you need to see the whole story. So for our final section, we're going to do just that. We're going to change our perspective and see how a different view can suddenly make the unseen visible. Take a look. On the left is the side view we've been studying, but on the right, that's an axial or top-down view. And all of a sudden, totally different structures pop out. See how the two lobes of the cerebellum are so clear at the bottom? This is why, to really get the brain's geography, you have to look at it from every angle. You know, maybe the most profound part of all of this is that we can go on this entire exploration. We can chart the very geography of our own consciousness without ever making a single incision. It's a true voyage within. And that brings us to the final biggest question, doesn't it? Thanks to technology like MRI, we can see the brain's physical structure in just breathtaking detail. We can map its highways and landmarks, but even after you've mapped the entire brain, the ultimate mystery is still hiding in there. How does all this physical stuff create the mind? How do these intricate folds produce a thought, a memory, or consciousness itself?
All right, today we are going on an incredible journey inside the most complex thing in the entire known universe, the human brain. And we're going to do it using only these remarkable black and white images from an MRI. Let's dive right in.
So what are we even looking at here? I mean, at first glance, it just looks like some kind of weird abstract art. It's almost impossible to recognize. But this mysterious landscape, it's a real place. It's a tiny part of the very thing that lets you see and think and feel. It's inside every single one of us.
It kind of makes you wonder, right? What if you could actually hold a map of your own consciousness, a map of your own thoughts? Well, that's exactly how we're going to treat these images. They're not just medical data, they're a personal atlas that we're about to explore together.
Okay, so let's officially start our expedition. Our vehicle for this journey is, well, it's a marvel of modern technology that lets us see deep inside the body without ever making a single cut.
So think of the MRI, the magnetic resonance imaging, as our camera. And the map it gives us is this series of digital slices. You can almost picture it like a flipbook of the brain. And we're about to turn the pages, one by one.
All right, let's start moving through the brain. We're going to begin right at the outermost edge and just work our way in layer by layer. But first things first, we need to get our bearings. The images you're about to see are what's called a sagittal view. All that means is we're looking at the brain from the side, as if we were taking these super thin slices, starting from one ear and going straight through to the other.
And here we go. This is our very first slice, right at the outer edge of the head. You know, at this point, we're mostly just seeing skin and bone, with maybe just a hint of the brain's shape starting to take form.
Now, as we move just a little bit deeper, the first real signs of those complex structures start to pop out. You can begin to see that distinct grooved texture of the brain emerging.
And there it is. Now that iconic folded surface of the cortex is coming right into view. This is the brain's outer layer, the part responsible for all that higher level thought, and its texture, kind of like a walnut, right? It's totally unmistakable.
With every slice, you can feel we're building momentum. We're moving steadily inward, from the side of the head and traveling right toward the very center of the brain.
Okay, let's just pause right here for a second. To get your bearings, look over to the left side of the scan. See that distinct, bright circle? That's the eye inside its socket. It's a perfect landmark to show us exactly where we are inside the head.
So we've moved past those outer layers, and now we've arrived at the core, the most complex and really the most densely packed region of the entire brain.
I mean, this slide just says it all, doesn't it? On the left, you've got that simple shape from the outer edge where we started. And on the right, that dense, intricate web we're seeing now at the very center. The jump in complexity is just staggering.
So, we've officially reached the brain's central processing hub. If you look down towards the bottom center of the scan, that thick, stalk-like structure is the brainstem. And right behind it, you'll see this finely lined structure. That's the cerebellum. People often call it the little brain.
Now, if we move just one single slice over, you can really appreciate how all of these deep structures are just woven together. This isn't just a collection of parts. It is a deeply, deeply interconnected network.
A great way to think about this whole area, especially the brainstem, is to picture it as the brain's central highway. It's the critical pathway where all the information from your body travels up to meet the higher processing centers of the mind. So, everything we've seen so far has been from just one direction. But, just like exploring any landscape, to really understand the brain, we've got to see it from some new angles.
We've been using that sagittal or side-on view. Well, now we're going to switch things up and go to the axial view. This is a totally different top-down perspective, as if we were taking horizontal slices from the top of the head right down to the chin.
And wow, what a difference a new angle makes. It is the exact same brain, but the perspective is completely different. On the left is that side view we're used to, and on the right is this new top-down view. It almost looks like a different structure entirely, doesn't it? So here's a single one of those axial slices looking up from below. This angle reveals this beautiful symmetry, and it clearly shows the brain's two distinct hemispheres in a way that just wasn't possible from the side. All right, we've traveled layer by layer, and we've looked from different angles. So for the final part of our journey, let's assemble all of these individual slices and see the full picture.
And here it is. This is that moment where our entire map is laid out right in front of us. Every single slice we looked at, and all the ones in between, each one tells just one small part of the story. But when you see them all together like this, they create a complete and frankly breathtaking portrait.
It really brings to mind that old saying, the whole is greater than the sum of its parts. We can analyze each little slice, but the true wonder is how all these layers of tissue come together to form a single, incredibly powerful functioning organ.
So we'll leave you with this final thought. We've just taken a detailed tour of the brain's physical structure, its folds, its pathways. We can point to every single part. But
Where, in all this intricate anatomy, where does a single feeling or a memory or an idea actually live? And that's the mystery that makes this journey so absolutely fascinating.
Okay, take a good look at this. What are we even looking at here? It kind of feels cosmic, right? Like something otherworldly. But what if I told you that this incredible landscape isn't millions of light years away, but it's actually inside every single one of us right now? So, let's start with a bit of a puzzle. Think of this as an abstract portrait, and we're going to slowly bring it into focus together. I mean, is this some kind of distant nebula that a super powerful telescope captured? A ghostly image from the absolute depths of space? It for sure has that mysterious, ethereal vibe to it.
Or could it be something way, way more intricate? Maybe a map of that 3-pound universe you carry around inside your head. You know, the source of every single thought, feeling, and memory you've ever had.
All right, let's start our journey right to the center of this amazing structure. We're about to go on a tour, but this isn't a place you're going to find on any map. Okay, mystery solved. What you've been looking at this whole time are images of a human brain, and they were captured in absolutely stunning detail by a magnetic resonance imaging machine, what we all know as an MRI.
So check this out. Each one of these images is like a single, paper-thin slice of the brain, and by just moving through them one by one, we can literally travel through the entire thing without ever making a single cut. It's incredible.
And this slide just shows that journey perfectly. So on the left, you're seeing a slice from the very outer edge. You know, we're just getting past the skull there. But then on the right, we are deep inside, right at the brain's core. You can just see how the structures change, how they get more defined, and how that inner architecture starts to reveal itself.
So the big question is, how is this even possible, right? How do we get such a crystal clear blueprint of what's going on inside our heads? Well, let's break down the amazing technology that makes it all happen.
Okay, and here's something really important to know. An MRI doesn't use any harmful radiation, not like an X-ray. Instead, it uses a super powerful magnetic field and radio waves to see inside you. It's just a remarkably clever and safe way to map our own internal world. Okay, so let's try to put this simply. Think of it like this. Your body is mostly water, right? Well, the MRI's huge magnet gets all the tiny protons in those water molecules to line up in the same direction. Then, a pulse of radio waves comes in and kind of knocks them out of alignment for a split second. And as they snap back into place, they give off a tiny signal. The machine picks up on all those signals and uses them to build an incredibly detailed map. And that map, that's the image we're seeing. So let's jump to a nice, clear central slice so you can really see how this picture comes together. You can easily spot the brain's main parts here. See that big, wrinkled out part? That's the cerebrum. That's where all our higher thought happens. Then, down at the back, you see that smaller, more tightly folded bit? That's the cerebellum, and it coordinates all our movement. And then, connecting everything to the spinal cord is the brainstem. That's what controls our most basic functions, you know, like breathing.
But here's the thing. These scans are way more than just beautiful maps of our anatomy. They're actually one of the most powerful diagnostic tools we have in modern medicine. They're used to find problems that are totally invisible to the naked eye.
See, by just tweaking the settings on the machine, doctors can create all these different kinds of scans. Some are great for seeing the basic structure, yeah, but others can highlight areas of inflammation or tumors or even track the flow of blood. That can reveal things like potential blockages or even aneurysms. All right, let's actually follow one of those stories. Put yourself in the shoes of a radiologist for a minute. You're looking at this scan, and it uses a totally different technique. It looks kind of noisy, pretty abstract, but you're not just looking at it, you're searching for a clue, something that just doesn't belong. Okay, now we move to the next slice, and it's like we're shining a different kind of light on the brain's tissue. Suddenly, certain areas start to glow. They begin to stand out from all that background noise. And just like that, the picture is getting clearer. The search is narrowing. You can start to see structures popping out that were completely invisible in that other type of scan. The hunt is on now for that one tiny detail that's out of place. And there it is. Bam! This specific imaging technique makes the anomaly, maybe it's a small tumor, maybe an area of inflammation, it makes it light up like a beacon. That is the power of MRI, the ability to sift through all that complexity and just pinpoint the exact problem with unbelievable precision. What we just looked at it's really nothing short of a modern miracle. It's a technology that has totally transformed how we understand the brain, both when it's healthy and when something goes wrong.
When you really get down to it, what we're looking at here is a map. It's the intricate, beautiful, and just impossibly complex landscape of what makes us us. And the ability to see inside ourselves with this kind of clarity and to do it without any harm, well, that's one of the greatest leaps forward in our whole quest to understand what it means to be human.
So today, we can map the brain's structure in incredible detail. But as this technology keeps evolving, what are we going to see tomorrow? I mean, we already have things like functional MRI or fMRI that can basically watch the brain at work by tracking blood flow. It can show us which parts light up when we feel happy or sad, or when we're trying to solve a tough problem. Other techniques are literally mapping the brain's wiring, all those connections between neurons. So you have to wonder, will we one day be able to map an actual thought or watch a memory being formed in real time? The journey into our own inner universe, well, it's really only just begun.
Have you ever seen a brain MRI? It's never just one picture. It's this whole collection of different black and white images. And you have to wonder, why so many? I mean, why not just one good photo? Well, let's dive in and decode what's really going on here. Right here, we are looking at the human brain. It's the most complex thing in the known universe. And thanks to this incredible technology, magnetic resonance imaging, or MRI, we get to take a detailed tour inside, without making a single cut. So this is our starting point. Okay, so the first thing to get your head around is that an MRI isn't a single photograph. It's much more like getting a whole portfolio of different maps. And each one of these maps is specifically designed to highlight a different part of the brain's tissue, giving doctors this incredible layered view of what's happening inside. Now, the technical term for these different maps is a sequence. And honestly, the best way to think about a sequence is to imagine it's a filter on your phone's camera. Right, you're pointing at the exact same thing, but when you change the filter, suddenly certain features just pop. MRI sequences do the exact same thing, but for brain tissue. So let's meet the first and probably the most fundamental map in our toolkit. This is called the T1 scan. And you can really think of this as the brain's architectural blueprint. So in a T1 weighted image, like this one right here, tissues that are high in fat, like the white matter that insulates all the brain's wiring, they show up as bright white. On the flip side, anything filled with water, like the cerebral spinal fluid floating around, that appears dark. This amazing contrast is just perfect for seeing the brain's physical structure, all its folds and distinct regions in stunning definition. Okay, so if the T1 scan is the blueprint for normal anatomy, then the T2 scan, well, that's the detective's map. It's specifically designed to find pathology, which is just a fancy way of saying it finds where things might be going wrong. All right, take a look at this side by side. On the left, that's the T1 we just saw. But on the right, that's a T2 scan of the exact same slice of the brain. See that dramatic change? The fluid-filled spaces that were black on the T1 are now brilliant white on the T2. And this is so important because a lot of disease processes, things like swelling, inflammation, even tumors, they involve an increase in water. So on a T2 scan, they light up like a beacon. So here's the crucial takeaway. T1 is great for anatomy, T2 is great for spotting pathology. It's almost like they're a photographic positive and negative of each other, at least when it comes to water. On T1, water is dark. On T2, and here's a little memory aid they teach in medical school, H2O is bright. Simple as that. But wait, it doesn't stop there. Beyond these two main workhorses, T1 and T2, radiologists have a whole toolkit of highly specialized sequences. You can think of them as advanced lenses for investigating very specific questions. For example, this is a flare sequence. It's a really clever twist on the T2 scan. See, it keeps all the problem areas bright, but it cleverly makes the normal cerebral spinal fluid dark again. This is super useful for spotting abnormalities that are right up against those fluid spaces, which might otherwise get lost in the glare. Now this next one, called diffusion-weighted imaging, it's amazing. It doesn't just look at how much water is there, it actually maps the movement of water molecules. See, when brain cells get injured, like in the first few minutes of a stroke, water suddenly can't move around freely anymore. This scan can spot that restricted motion instantly, which makes it one of the most powerful tools we have for catching a stroke early. And then you've got this lens, susceptibility-weighted imaging. This sequence is incredibly sensitive to tiny changes in the magnetic field caused by stuff like iron. And since our blood is full of iron, this scan basically acts like a magnet, making even microscopic spots of bleeding or old iron deposits
pop out as these really distinct dark spots. Okay, so we've got all these different maps, and each one is telling a different part of the story. But there's another piece to this whole puzzle. How do all these flat, two-dimensional images give doctors a complete three-dimensional picture of the brain?
Well, the key is to realize that every single image we've been looking at so far is just one super thin cross-section of the brain. The best analogy? Think of it like a single slice from an entire loaf of bread. So for any given sequence, like this T2 scan here, the MRI machine doesn't just take one picture. It acquires a whole stack of these slices, maybe moving from the bottom of the brain all the way to the top, or from the front to the back. The process itself is pretty simple, but it's so powerful. First, the machine gets dozens of these 2D slices. Then they're all stacked up in the right order. This lets a radiologist just scroll through the stack on their computer, and in doing so, they can move through the brain as if it were a complete 3D object right in front of them. All right, let's bring this all together. The real diagnostic power of an MRI, it comes from combining the information from all these different views, all those different maps, and all of those different slices. So, a radiologist will look at the T1 to understand the basic anatomy. Then they'll check the T2 and the flare for any of those bright spots that could signal a problem. Next, they'll glance at the diffusion scan to rule out a stroke and the susceptibility scan for any signs of bleeding. You see, each one provides a crucial, totally unique piece of the puzzle. So why so many pictures? Because each one is a different layer of information. And when you stack all of those layers together, the anatomy, the pathology, the water motion, the presence of blood, you get this rich, multidimensional, and incredibly detailed landscape of brain health. It's not about one picture, it's about getting the whole story. And that brings us to one last, kind of mind-blowing thought. We can now map the physical structure of the brain in a way that was just pure science fiction a generation ago. So the real question for the future is, what's it going to take for our maps to become so sophisticated that they can show us not just the brain's structure, but the actual shape of a single thought?